All right, so today we're going to talk about energy stored in capacitors. And so this is an image of a calculator. And so the calculators are battery operated, but you have to store certain things in memory, and they can use capacitors to do that. Capacitors can actually store a charge. This is why when you take apart electronics, you have to be careful, because even if it's unplugged from the wall, and even if you have no electric source to it, the capacitors can still store a charge. And this is what they're used for. Now, capacitors kind of look like this or this, and these aren't the only two variations. These are the most common ones. So I circled them. This is a capacitor. This is a capacitor. In these, you have the two plates separated by something that separates them. That's the best way to word it. And then these are a capacitor where there's an inner plate and an outer plate, and those are separated, and they're kind of shaped like this. So I think this is a capacitor. It's hard to tell. I know this is a capacitor, and these two are definitely capacitors. And so they hold charges, and that's basically what we're going to talk about today, is the energy stored in a capacitor. So there's a couple of things that I want to review before we get started, but energy stored in a capacitor is electric potential energy. And so there's this relationship of electric potential energy where we, whoops, wrong color. Let's change the color. Where we have the change in potential electric energy is equal to the charge times the change in voltage, right? And then, well, if the capacitor starts with 0 voltage and gradually comes up to full charge, then the full voltage is the actual charge. So the first charge placed on the capacitor experiences a change in voltage, since the capacitor has a 0 voltage when uncharged. So the final charge, in other words, delta V, if you want to think of it this way, delta V is equal to the final voltage minus the initial voltage, but the initial voltage in most cases would be 0. Now, that isn't always the case, but when we think of a capacitor, you have to charge it, right? So then what does that mean? Well, that means that the change in voltage is just the voltage, okay? If you want to think of it that way. Since the capacitor now has a full voltage V on it, the average voltage on the capacitor is 1/2 of that, right? So let's talk about that. So if we say V average, because it starts off at 0 and works its way up, so that's just going to be V divided by 2. And so the energy stored in a capacitor is actually equal to the charge times the voltage 2. Oh, and I think I skipped over Q, right? So remember that the charge capital Q and the voltage V on the capacitor, right? And then also remember that basically we're going to replace the potential electrical energy lowercase q with a capital Q, right? And we can calculate those Q's. So we covered that a while ago. So this is the energy stored on a capacitor. This is the beginning phases of that, right? And so then also remember that QV, or the relationship Q, remember that Q is also equal to CV, right? The capacitance times the voltage. So if I take the same equation up here, in other words, if I start with this equation, the energy of a stored on a capacitor is equal to capital QV divided by 2, and then I replace this in for Q, right? I get CV times V over 2, which is actually CV squared over 2, right? And then you can, this is the tricky part, and I'm going to write it down and then we'll figure out how you how do I say this? So if I say Q, actually I'll write it out first. If I say Q squared, then I really have CV squared, which is just equal to C squared over V squared, right? So in this next line, if I multiply the top by C and I multiply the bottom by C, and then I have this V squared, in the very next line I have C squared V squared over 2C, which is really Q squared over 2C. So another way that we could calculate the energy stored in a capacitor is we have the charge Q squared divided by 2 times the capacitance of the capacitor, right? So what does that mean? Well, that's basically it. Q is the charge, V is the voltage, C is the capacitance. And so this is a little easier because usually we'll know the charge and the capacitance of a capacitor, and then we can calculate the energy stored. The energy, of course, would be in joules. The charges would be in coulombs, and the voltage would be in volts, and then, of course, the capacitance would be in farads. So what does this mean? Well, let's take a look at an AED. So AEDs actually operate on this same principle. So an AED, if you're not familiar, is it's a machine that's automated. It's for a regular person to use if somebody has a heart attack, but it shocks the heart and restarts. It's what we call a heart defibrillator, but it all does it automatically. And so an average person can just pick it up, plug it in. It's a brilliant engineered item that saves lives every day. But basically, you just hook it up to somebody's chest, and it'll measure their heart rhythms and then give the appropriate charge if it's necessary. Okay, obviously you should always call 911 and do CPR, but this is the math behind calculating those charges and what you need to do. So a heart defibrillator can deliver 4 times 10 to the 2 joules of energy by discharging a capacitor initially at 1 times 10 to the 4 volts. What's the capacitance? So essentially you need a capacitor, and what's interesting, it'll say charging and then it'll say clear. So what it does is, and these just have batteries in them. So the battery will charge the capacitor. The capacitor has to be designed specifically to deliver this voltage or this energy and voltage. So you got to figure out what's the capacitor, what's the capacitance of the capacitor. So the battery charges the capacitor, and then when it goes to deliver the shock, it discharges the capacitor. Essentially, that's how it works. So to find the capacitance, we start with our equations where we say that the energy stored is equal, I hate when that does that, is equal to the capacitance times the voltage. And so this would be our energy, this would be our voltage. Oh, wait, that's over 2, right? So in this particular case, we'd use this first equation. So my energy, now what I probably could do is rewrite this. So if I solve for capacitance, That would be 2 times the energy of the capacitor divided by V squared, the voltage squared. Right, and all I did is some algebra. I solved for V. I multiplied both sides by 2. Right, multiplied this by 2, multiplied this by 2. These 2's canceled. And then to get capacitance, I had to divide by voltage squared, and whatever I did on one side, I had to do to the other. And so that's how I get this equation over here. Okay, so I plug that in, 2 times the energy, which is 4 times 10 to the 2 joules, divided by the voltage, which is 1 times 10 to the 4 volts, and all that would be squared. And so when you get done with this, you get the capacitance is 8 times 10 to the negative 6 Faraday, farads, I guess, which is 8.00 micro Faradays. Okay. And that's basically it. Now, this is basically how it works. So if you have a capacitor that has this rating and you fully charge it up, when you discharge that energy, it will give you this amount, or how do I word this? It will deliver this many volts based on the energy that's stored. Okay? And it can regulate the charge too. So that's what's cool about that. So, and that's basically it. So there's just 3 assignments, or I think it's 3 or 4. I think it's 63 through 67, which I think is 4 problems. That's it though for today. And then we gotta get ready for a test.
Okay. Yeah. You're right.